So to start off, I just want to revisit that example we did last class with the sets that we did. We used an example to not prove, and then I asked you guys did you guys come up with a proof? Like some that didn't use an example to show that they were the same? I think it's an important example because one, it introduced the notion to us of a counterexample where we can actually use a specific example to prove some claim, as well as it has also more rigorous proof. I shouldn't say more rigorous, but a more general proof that doesn't rely on examples. And I think just the search for it is actually a very good thing for us to be exposed to. So we started out, you picked an example, did the example, so that's what a counterexample is. You can come up with an example that disproves some statement, you're good. Okay, so you can know that it's not true. Now let's actually talk about arguing, right? And figuring out when something would not behave the way you want, right? So let's say for some reason you had suspicion to expect this is true, right? And that sort of makes sense because you're like, okay, if a coordinate is in here, it means the x value is not in A and the y value is not in B, right? So if I say here, if there's a coordinate in this guy, it means that, well, your x has to be in the complement, your y has to be in the complement, which means that your x is in particular not in your A and your y is in particular not in your B. So it makes sense that the coordinate xy should not be in the coordinate A cross B, and so it should be in the complement, right? And you look at that and like, well, that equation kind of makes sense to me. It turns out it's not true though. And does anyone see why that's not true based on what I just said? Yeah. But what am I missing? Why is that the reasoning process that I just went through? Why is it not enough? Why is it that it led me to a false conclusion? Because we know it's not true. We actually did an example, right? But what was wrong with what I just said, though?
Oh, you begged the question.
Did I?
Oh, no.
No, I said, oh, if a coordinate is in here, that means the x must be in that set, the y must be in that set. That's definition. Then, if it's in the complement, it's not in the set. If it's in the complement here, it's not in that set. Which means that coordinate would not be, right? So that means, ultimately, that xy is not going to be in AB. Which means if it's not in that, it must be in its complement. That makes total sense to me. Yeah?
The A cross B, or rather the complement of A cross B, would it not potentially contain elements where one is? I was saying potentially it could contain an element where.
So you're saying this guy could contain something that's not over there?
Yeah.
Okay, so that was the mistake. Because what I said here actually did make complete sense. I didn't make that up. Right? If you're looking at that, what did he say wrong? I didn't say anything wrong. The important thing is, what I said was this relationship. And it turns out that that's actually true. This is a subset of that. What is the problem? Why equality breaks is because it's not correct to say it the other way. It turns out that this is not a subset of that. It turns out that this guy could potentially have things that that guy doesn't have, right? And so one thing goes back to the importance of definitions, knowing what does it mean to be equal. You're never going to talk yourself into something that's not true because you always obey a definition. When I made this argument, I made complete sense, but that argument was for a subset in one direction, which means I should not convince myself of an equal sign by arguing half the equal sign. I have to be able to argue both ways. And it turns out when you start arguing the other way, that's where something is going to break, right? Now, and again, let's go to the statement. For some reason, I believe that this was true because I thought of this in my head. And so now I'm thinking, would it actually go the other way? And how did we actually look at this, right? So when we looked at this, so this is going to be a repeat of yesterday, pretty much. We actually fleshed out what this actually meant, and we write it down as sets and came up with two statements that would make it true, right? So we said this was the complement of the set of all xy such that, and of course the xy are in some universals cross of u cross u. And this might be the universal set for A and the universal set for B. They could potentially be different, but whatever. Let's not get too much into that. So this is the set of all coordinates in this universal set such that x is in A and y is in B. And we're taking the complement of this. Right? So what does that mean? It means then, I'm talking about all the set of coordinates, and you can even think of this as me applying De Morgan's law for some reason, such that either the x is not in A or the y is not in B. Right? So basically I'm just talking about, if I'm looking at values here, the important condition is my x is not in A or my y is not in B. Now over here when I'm looking at this is the set of all coordinates. Right? They could be different variables, but whatever. Such that x is in the complement and y is in the complement of B. But that would mean that x is in A complement and y is in B complement, which would mean that my x is not in A and my y is not in B. Now, obviously now you start to see differences start to arise. This guy has an or. This guy has an and. And because we're super paying attention to detail, for us that is very different. This or is the inclusive or. So it turns out the or would include the and, which is verified by our reasoning there that the subset does work in one way, because the or includes the and. But and does not include or, because there are situations where or would work where the and won't, right? And requires both things to be true at the same time. Or requires either or to be true at the same time, with the potential for both to be true at the same time, right? So this is a much broader thing to get to work than that, right? So now we can start to use pictures, right? So I'm investigating this claim that may or may not be true. I'm not completely sure. It seemed to make sense to me that it was true, but I'm not sure. So I went back to the definition. What do these guys mean? So I get these two statements and I'm like, there's something different here. Let's actually represent that with a picture, which I also think we did yesterday. So let's say that's A complement, that's B complement, right? Which is weird, I'm drawing them not sets, but and here, that's my A complement, that's my B complement, right? So the coordinates that deal with this guy are the coordinates that live where? Where do they live on this picture?
Which guy?
In this guy. Right? Which means my x is in A complement and y is in B complement. Where in this picture do they live? So this is like going back to homework 1, where you actually have to draw pictures of the sets. The overlap, right? They would live here. Right? So coordinates in this guy live in this space. What about this one?
Above the circle.
Everywhere, right? So they would live in this space as well as in those two spaces. So now I'm starting to seeing a picture. And a picture is not a proof, right? Because a picture is not a statement. Different people can look at pictures and come away with the same thing. Pictures have to be interpreted. They're not declarative statements. You can't say that picture is true or that picture is false. You can't really say that. So pictures aren't proofs, but they can indicate to us ideas of where we want to go. So at first glance, this seemed to make sense to me, but that was because I wasn't being too rigorous. Now when I start to put it in a picture, I'm like, now I'm not so convinced anymore. But how would actually disprove it? Well, I know that if I pick anyone in the overlap, things are going to work out. So let's deliberately pick someone who's not in the overlap, right? Let's either pick someone who's here or pick someone who's here, right? And see what happened to that guy. So I'm not picking a specific example right now. I'm just thinking of, in general, as an idea, what would the points in here behave like in terms of this, and what would they behave like in terms of that? So, which one do you want to pick? It's actually not going to matter. The proof is going to be like very similar.
The one B complement.
Sure, let's pick that guy. Doesn't matter, right? Now let's focus on that guy. Now, what about this point? Tell me where it lives. Right, so if I call that point Z, right? It is an element of B complement. Right? In terms of the set A, where does it live?
In A.
It's in A. How do I know it's in A? Because it's not in A complement. Okay. So now let's look at points of that nature. Things that I'm going to pick a coordinate where one part is in A but the other part is in B complement, and I'm going to try to see that that relationship doesn't work. So let's actually do that. Right? So we're not going by an example here, we're going by a general proof that I got the idea for that proof from the picture. Let xy be such that the x is in A and the y is in B complement. Right? So I'm thinking this, yeah.
It's so confusing because of the inverted worlds.
Wait.
If it's not in B complement,
It's in B complement because this is the B complement circle. So it is in B
it's
complement. However, it's not in A complement.
Does that mean does it immediately mean that it's in
Yeah, because they're in one or the
A?
other.
What if it's in the outside universe, like outside?
The outside universe is in A.
Alright.
Right? There are only two regions, right? If you were to draw a picture, let's say there's one set here, that's A, and there's one set here, that's A. What is A if you were to shade it on the picture? Well, it's this guy. What is A complement if you have to shade it on the picture? Everything else. In other words, the universe is, you can always think of it as being a set union its complement. Because when you put them all together, you get everything. So if you're not in A, you're automatically in the complement. If you're in the complement, you're automatically. If you're not in the complement, you're automatically A. This is. So I'm not in the A complement circle, which means I'm in the A circle. I can only be in one place or the other.
But there would be an outside circle, right? In that picture.
Yeah. So I mean, if you want to imagine it, there's like probably this broader set here that you can think of as an A. But I wouldn't worry about that too much. I think going by the pictures here is definitely important. The important thing is, I'm focused on the complements, so I'm thinking of the complements as sets in their own right. And the pictures didn't seem to match up by me drawing them, which makes me immediately start to lose confidence in this thing. So let's actually see if we can prove, not by a picture, but using statements logically derived, that this equation will break. And my idea is to use something where the pictures were different. And so let's actually see if that worked out. So I'm going to pick someone who's in A and B complement, which describes that point here. Okay. So notice here then, if my x is in A and my y is in B, I know the following. xy cannot be an element of A cross B. Right? Because this guy has people where the second coordinate live in B, but I know for a fact that my second coordinate is not in B. Which means that my xy must be an element of the complement of A cross B. Right? So I conclude that my xy is in this guy. But I claim that xy is not in this value. Why?
Because your A can't be.
Because
your x cannot.
this is claiming that my x is in A, but I know my x is not in A. Since my x is in A, so x is not in the complement. So I have found a coordinate that is in this set, but it's not in that set. What did I just prove? Not equal to, but more immediately, what did I just prove? That something is not a subset. I just proved that something is not a subset of someone else. I just proved that A cross B bar is not a subset of A. Because there could be an X in here and it does not imply that it's in there. Which now, more to what I care about, that implies that A cross B complement is not the same as A complement cross B complement. Now, this is an important example because a bunch of techniques can be used here that are all important, and a certain kind of reasoning can be used here that's also important, that we're going to touch on again when we talk about prove or disprove. We're going to do that. So there's going to be a chapter in our book where they just throw out a bunch of statements to you and they don't tell you if they're true or false. You kind of have to figure out if they're true or false and then prove what you think is true. Okay? So, which that happens, right? It's not, especially like for those of you who are going to be math majors and you're going on to research, you're going to be encountering things that I don't know if that's true or not. I don't know, right? There are going to be times when you don't even know what questions to ask until you encounter something that you're working on. You're like, okay, I want to be able to say this in order to make something work. Is that true, right? And you might think to yourself quickly, oh, it seems to make sense that it's true, but you have to be sure that it fits the definition, right? So then you start to really dig deep into your definitions, and then you kind of see, well, there's something not right here, right? And then you go to prove that. And you can disprove something by using an example that we call the counterexample, which we'll talk about in the next chapter. Or you can actually reason logically and actually write a proof that something does not exist. And one or the other may be easier, but they're both equally valid. But that's an important idea, the idea that you can encounter something that you're not sure if it's true or not. And how would you go about in figuring that out? Turns out the guide, as always, is our definitions, which is why that was the first 3 things that I told you had to know in order to do well in this class, is to know the definitions. Because if you don't know definitions, it's going to be easy to lead yourself astray. You convince yourself of things that are completely false because you don't fully appreciate what it means for the definition, what are all the pieces that need to fall into place in order for something to work. Yeah.
Question follow-up. Would it also be allowed to, if we did like a constructive proof, and then just from that picture, like after using the definitions, just choose one that's exclusively in the A complement, or one that's exclusively in the B complement? Would that work?
Yeah. I mean, that's kind of what I did, but I made that jump after writing down the picture, right? But if you saw that before the picture, then that's completely fine.
Okay.
Right? At the end of the day, we had to start with the definition, and the definition implied certain things have to work out, and the fact that one had an or and one had an and, that kind of suggested to me that, you know what, there might be a case where these don't work out. Because this would include that, but this does not include that. Yeah.
Is there a reason that the and, you started with and then you more?
Because it's a complement. This set here, I took a complement,
Oh.
and we already know by Morgan's law that the complement of an and is an or. The
I
complement
thought you were
of
on
an
line.
and.
Yeah.
Yeah, no, those were De Morgan's laws. So these are things we know, so we can assume at any point. There are De Morgan's laws for sets. I don't remember if I wrote it down, but it's definitely true. If you take the complement of an intersection, it's the union of the complements, and if you take the complement of a union, it's going to be the intersection of the complements. These are De Morgan's law. It's also that thing where we're negating statements, and I said the negation of P or Q is not P and not Q. So you can always negate an and, you get an or. If you negate an or, you get an and. That's something that we always do. But this was a very nice example because there's a lot of currency here. It teaches us a lot of lessons, some hard lessons, and the fact that it's easy to lead ourselves astray if we don't know a definition, if we're not sure if something is true or false. How do we unpack things to be able to suggest to ourselves what is the right approach to take, right? So it turns out that if I wasn't sure if this is true or false, it made sense for me to assume that it's not true. And so I would spend my time trying to prove it's not true, as opposed to trying to prove it's true. I don't want to spend years of my life chasing something and then to realize, oh yeah, it actually doesn't exist, right? It's not where you want to be. So that this is an important definition for that reason. As well as an alternative way that's just as rigorous is to just choose a specific example that makes it false. And we actually did that last class, so I'm not going to do that again. The principles of choosing examples, keep it simple, right? Don't choose all the numbers from 1 to 10 because you have to write down a bunch of coordinates that you're not going to need. It's just going to be tedious to write down. So you start keeping it simple. If you realize your simple examples can't cover all the possibilities, then you start inching them, making them a little bit wider, right? So you...
Do equal statements have to be handled like if and only if statements in most cases? Will that both sides or both sides have to be true in both directions?
We will answer that more completely. In equal depends on context, right? And we'll understand that more when we get to chapter 8. For equality of sets, if I'm talking about equal between sets, then yes, it is an if and only if statement, right? And oftentimes that will be the case, that it would have to go in both directions, right? When we get to chapter 8, we'll talk more about equality and what it means to be equivalent in some sense, and we'll get to that. That property that we're talking about is the property of symmetry, where something has to work in both ways. We call it symmetry, and we'll discuss that in chapter 8. But yes, usually with an equal sign, that's the case. It's also important, and this came up in my 346 class yesterday, that when in mathematics we say this is equal, right? What kind of statement is that? How do you say, like how comprehensive is that statement?
Extremely?
Huh?
Extremely?
Is it extreme to say something is equal or not equal? For example, well, sometimes it can be extreme. I can say something like, this guy is not equal to that guy. Right? A mistake students often make, but whatever, let's actually look at it. If I say x, y, and r, and this is not true in general. So when we say not true in general, what is that? How do you interpret that?
There are some cases where it's true.
There might be cases where you might be able to get away with one case, right? Where you can like, okay, let's just choose the x equals 0 to the y. X equals 0 and y is positive, it turns out that would be true, right? But if I say, I don't say in general, but I say something like, if x not equals 0 and y not equals 0, right? The thing is sometimes when you make a statement, it's not to say that it always will work or always won't work. There are always conditions that you have to worry about. The conditions are important. The assumptions under which you're making a statement are important. So there was an example that I showed yesterday where I said, we can't assume that these things are equal. Like when we're in linear algebra, and we're saying, if these guys are matrices, then we will assume that this is the case. But it turns out you can actually find matrices where that's where the equality, they do come in. But as a general claim, you have to understand. What it means is, there might be a few cases where the thing works out, but there might, in general, you cannot make that assumption. It goes by a case-by-case basis. So here when I said, show in general that this is not equal to that, that can kind of mean, we can probably come up with some sets that make a stupid example where they are equal. Like, if we choose A and B are the empty set, then, you know. But you always want to know when a statement is being made, what is the scope of that statement? How comprehensive is it? So, I spent more time on that than I should, but there were a lot of important lessons in that example. If all goes according to plan, we'll end this class with also a very important proof with a lot of lessons. And it'll be the most important proof we do so far this semester. Let's see if we can get to it. And I'll tell you why the proof is so important. Well, it should be obvious why the proof is so important. But I'll explain why that proof is so important when we get to it. For now, let's move on to chapter 5, where we're going to explore this idea of counterexamples a little bit more, as well as do proof by contradiction. Existence. And proof by contradiction. Start with existence. That's an important thing, because that means there's an example of some concept that you're talking about, right? And knowing whether or not there exists such an object that fulfills some property or definition or concept that you're talking about is important, again, because you're not chasing something that doesn't exist. You want to know that something exists or not, so it's worth chasing or not, right? So existence is a very important thing, and so how about these some examples? The general idea let me just actually write this down here. So this is a general statement that we want to be sure. One is make sure when we can know how to use examples. You can use an example to. This is when you're allowed to use an example. It's a very important idea for you to worry about. And we'll talk about that a bit later as well. Right? Here's when you are allowed to use an example. Does anyone know? Give me one reason where an example is allowed and it's useful to use.
Trying to prove something exists.
When you're trying to prove something exists, to prove an existence claim. That's it, right? This, by the way, is a claim that something exists. A claim that an object exists that fulfill some desired properties. So if I made the claim, leprechauns exist, all you have to do is show me one leprechaun. Present one example of a leprechaun. And I'm like, yep, leprechauns exist. You can't argue with that, right? So I can give you an example that fulfills a certain property. That is the proof of the existence of such examples, right? I can say, this exists. How do you know? Here's one, right? It's right there. You're seeing it. You have produced an example. You can use examples in that way to prove existence claims. And existence claims are very important. They're claims about the existence of some object that fulfills some property. How else can we use examples? Counterexamples. How would you describe using that? We used it in the example that I brought up today from last class. You can use these to disprove.
Leprechauns don't exist.
No, how would you do that?
Show you one. Or I guess that would.
Oh, to truth. Oh, you're. Okay, I see where you're going. Okay. To disprove universal things. So a universal claim is something that claims to be comprehensive. You can say, nowhere in the universe there are leprechauns, and then someone shows you, this is a leprechaun. Fits the definition, right? You can give me an example that disproves a general claim, right? So there's some sort of universal claim about non-existence, usually. All you have to do is provide an example. It's not always about existence or non-existence, but you can use it to do things like disprove a claim. So you can either prove the existence of an object by using an example, you can disprove a universal claim by using an example. In this case, the example is called a counterexample. Because it counters some claim that is made. Right, so to the, so for example, to show that A cross B equals A, or B cross is false, we use the counterexample. Where we picked a set, U was, I believe, 1, 2, 3. Our A was 1, 2. And B was 3. Was that it? Or something similar to that. So we have a general statement here that someone says, oh, this is equal to that, right? But to prove that that's not true, to prove that's false, we could make a counterexample. So there was some general claim of equality. They said, in general, this is equal to that. Well, no. We can use an example to disprove that. It's equally important to know when you cannot use an example. This is the one that students usually mess up on. There are a lot of times where I ask students to prove something in general, and they just give me an example. I'm like, okay, that's cool, but you have to show it in general. So there are times, and again, for those of you in linear algebra, there are times where I say, prove that this is true for matrices. And then they show me an example of 2 by 2 matrices. I'm like, I didn't say 2 by 2 matrices. I said matrices, right? But they gave me this example. Oh, it works out with 2 by 2s. That's cool. That's not what I asked about, though. Right? So you have to be careful when you cannot use examples. Okay, when can you not use an example? It's pretty much going to be the converse of those guys. Right? So we can use it to disprove a universal claim, but it turns out you cannot use it to prove a universal claim.
Unless there's like one element in the universe, right?
I guess very true. You cannot use to prove a universal claim. So if I say this will always happen in this broad category, and you show me one particular example to say that, so an example is, example. So you can say things like,
All even numbers are prime.
yeah, but I think I said that already, right? So we can be like, well, 3, 5, 7 are prime. So this means all primes are odd, right? You can make that conclusion, and you can keep going, by the way. But yeah, you forgot to pick, this is obviously wrong, since 2 is prime. Right? But someone starting from 3 can literally give you an infinite number of examples of odd primes, and they can convince themselves that all primes are odd. But the thing is, any finite amount of examples you give to me cannot prove a universal claim, like all primes, right? It says all of them. Really? Right? So you can't prove a universal claim, because there are times when you'd be able to offer an example for this or that or this or that, but sometimes you didn't pick the right example. So you can't prove universal claims with an example. You also can't disprove existence claims. Right? So if I make a statement, leprechauns exist, you can't prove that I'm wrong by just showing me a bunch of things that aren't leprechauns. Right? Look at this, it's small, it's not a leprechaun. Look at this, it's not a leprechaun. Look at this, it's not a leprechaun. Leprechauns don't exist. You didn't prove leprechauns don't exist, you just haven't found one yet. Someone will always be able to argue with you that, yeah, but you didn't look over there. Or, okay, you go look over there, oh yeah, you didn't look over there. Like, you can't show me an example to prove that something does not exist. Or it doesn't make any sense. Right? So that's very important. So existence is an important thing because sometimes we want to know that there is an object that fulfills a certain property that we care about, so we don't waste our time looking for things. And examples come in handy with existence, but you have to be sure that you're using an example correctly. Most of the times we use examples, it will be used in this context as a counterexample. So if there's some universal claim that you want to say is not true, all you have to do is produce one example. Right? So if I say for all of this, this is true, if you can show me there's at least one where it's not true, then that example is useful and it works. And why does it work? Because of the negation, right? So we know the negation of for all is there exists all. So that's very important, how we can use examples. Let's actually do a few examples with that and then jump to proof by contradiction. There is no positive integer such that x is the sum of its proper divisors. Make it easy for you. Disprove this. So the claim is actually not true. Do we know what proper divisors mean? Okay, so A is a proper divisor of, it's kind of combines the definition of a divisor and a proper subset, which means not less than. Okay, so a divisor of B if A divides B, but A is less than B. Right, so it's just example 2 is a proper divisor of 4. So is 1, right? So the only proper divisors of 4 is 1 and 2. Anyone think of an example? 4?
The counterexample? Like an example?
Yeah, an example that shows that that's not true. There is
Oh,
a
yeah.
positive integer.
Well, like 6, 28, like 6.
6 is an example, right? So I can give an example to disprove that claim, right? 6 is equal to
1 plus 2.
1 times 2 times 3. These are all proper divisors. And 1 plus 2 plus 3 equals 6. Right? Take all the positive integers that are less than 6 that divide into 6, and if you add them, you get 6. Right? And as you said, 28 is another one because 6 is an example of, what are they called?
Perfect.
Perfect numbers. This is actually a thing. It's one of those things that some mathematicians geek out about. Oh, let's find all the perfect numbers, you know, like, let's find all the primes. How do we know? Let's find another prime. You know, there are people like that. There are people who are obsessed with perfect numbers, right? So it's a whole category of numbers, and there are a lot of them. So there is such a thing as a perfect number. This is a number that is the sum of its proper divisors. So it turns out if someone said, "Oh, there's no such integer," you can just give me an example, like, yeah, now shut up, right? It shuts them up. Like, okay, yeah, cool. You didn't even have to go that far. 6 is not that high. So that example wasn't so bad. We're going to use an example that's, well, several more examples. Now I'm going to claim that there exists something. There exists A and Q and B and I such that A raised to the B is in Q. In fact, I don't think I defined that before. I am talking about is equal to the set of irrational. Irrational real numbers, right? The real numbers that are not rational. So I'm saying this is the set R minus Q. Right? All numbers on the number line that are not fractions. Okay. Can you give me an example to prove this claim? So you can actually prove that this claim is true with an example. Why? Because it says there exists. It's not a universal claim. It's an existence claim, which means once you can find one example, it's true. Give me an example. Take A equals this, B equals that, then the claim equals, and you can prove it then. Okay, so A, the base, has to be rational. The power that I raise it to has to be irrational. But when I take them as a whole, it's a rational number.
One to any irrational number?
1 to literally anything. 1 to radical 2. Right? There are many. You can use 1 to any rational or 0 to any. Yeah. You can say A is 1 or 0, and B is, you can pretty much choose on a whim. Right? And that is a proof of the claim. There exists such a thing because I just gave you one. 1 to radical 2. 1 raised to the radical 2 is 1, and that is rational. Here's a little freaky one. Someone actually asked me about yesterday, which we're going to talk about it, because it's an important kind of way that you can sneakily give an example, but it's completely logically valid to give an example like this. And you'll see this from time to time in mathematical literature, so I don't want you to be freaked out about it. It's another existence claim. It's like that one, but it takes things to a dark place. There exists two irrational numbers, a and I and b and I, such that a raised to the b is in Q. So yeah, this wasn't that bad. You guys came with an example right away. Give me an example here. Is that my computer or is that something else? That ding that keeps going. Oh, that's you? Can you turn the sound down, please? You want to think of that example? Yeah. Pi to the e. Pi to the e. You think that's a rational number? You can write that as a fraction?
You can try.
Huh?
You can try.
I can try? It actually exists. It is a true statement. Now, the example is going to be weird, but I want to. So this will do two things. One, I'm going to introduce you to this weird way to construct an example. And two, I'm going to introduce you to literally the most scariest word in all of mathematics. Like, this is hands down the scariest word you will ever encounter in a math textbook. Proof. Consider. When you see that word, be very afraid. Consider, ponder, think about this. Right? Whenever you see something starts with the word consider, it means that the person is going to pull out this random example where you're like, how the hell did you come up with that? Like, where did that come from? Where's the logic? Right? It's kind of like when a math person doesn't really know a logical way to get to the answer that he got to. It's like, consider this. Clearly this is an answer. Yeah, but how did you get that? Just consider. Yeah, so when it's consider, something that's going to follow that is going to be something that's going to spend you hours of your time to figure out, or you'll never figure it out, like how they came up with that example. But consider this number. A equals radical 2 to the radical 2. And now you're like, okay. How do I know that that's fulfills the claim? Now they're going to hit you with a statement like this. Either this is rational or it's not. Right? So they throw this random example there and they say, you know what? This is an example of what you're looking for. Or maybe not. Right? Kind of like what she tried to pull on me just now. Pi to the e, and I was like, oh, is that a fraction? I don't know, right? That's what they're doing right here. They're like, consider this example. It's what you're looking for, or maybe not, I don't know, right? Now, that's it. Now, why are they allowed to say that statement, right? Because it seems very cheeky.
You're not wrong.
That's the exclusive statement.
Why is this? This is true. Why is it true? It's a tautology. We looked at this before. What they're saying is P or not P. That's a tautology. A math person can literally make a statement like this at any point in a proof and you cannot fault it for it. This is it or it's not. Okay, that is logical. You just said a tautology. This is either rational or it's not. That is true. How does that help me? Okay, so now they're going to say, if it's rational, we're done. Right? Now, they're saying radical 2 is clearly irrational. We'll prove that, by the way. And so I just took an irrational number, raised to an irrational number, and I got a rational number in the event that it's rational. Right? So if it's end up rational, we're done because I found an example that fills the claim. If it is not rational, though, right? So basically they throw out a tautology at you. Either this is what you're looking for or it's not. If it's what you're looking for, good luck. I just gave you what you're looking for, leave me alone. right? If it's not what you're looking for though, now they have to give you something extra to fix it. Now, given that example, does anyone see how we can fix that? I want to raise that to an irrational number and obtain a rational number. Raise it to the radical 2 again. I know that radical 2 is irrational. Then, take b equals radical 2. So we get a to the b would be equal to radical 2 raised to the radical 2, and under the assumption that this is not rational, meaning it's irrational, I can raise that to an irrational number and end up with a rational number. So this is kind of a sneaky way to give an example, but it's completely logical because they use the tautology on you. They're like, either this is what you want or it's not. That is true. If it's what you want, we're done. Now, we're done here. And if it's not what you want, here's how you tweak it to get what you want. Right? And they gave you a perfectly logical example. And it's kind of like, it's on the border of an example and a proof at the same time, because they threw an example out there, but what they illustrated to you is the idea that such a thing could exist, right? Because you don't actually know if this fits the rule or not. You don't know, right? But they're like, it either fits the rule or it doesn't. If it doesn't, this fits the rule. So it's kind of like giving an example without giving an example. It's kind of like you're proving an example exists without being too specific. But it's a common type of example to give in a math context. And these statements are very common as well, but there are tautologies. So whenever you see them, don't be weirded out. Whenever you see this word, just be very afraid. Because then I threw that out and you're like, oh, what the, okay, right? That happens a lot as well. But it's completely logical to give an example in this way. So that's a very important example. That will either help you in writing your own proofs or giving your own examples, or at the very minimum, when you're reading someone else's proof of an example, the existence of an example, you'll recognize this technique as something that is done, and something that is not actually cheating. It's cheeky, but it's not cheating. It's still, it's correct. Let's move on to proof by contradiction. I'm not sure I'll get to the other proof later. Right, now this is the most trendy kind of proof there is. I say that because students love using this kind of proof for some reason. Everyone, even now on homeworks, I see people doing proof by contradictions and we haven't covered it yet because the young people love it. Right? It's a thing. Like everyone, like they like being rebellious. You know what? I'm going to contradict that. Go against the establishment. So they kind of prove something by proving not something, and that's kind of There are also a lot of mathematicians who don't like this. Of course, they're usually the older people, the purists. Never use proof by contradiction. But it's a valid way to prove things, and I'm going to show you how it works. Let's actually justify it based on logic, right? So its use is grounded in the idea of truth tables, which we know is where our logic comes from. So let's do that. Let R be a statement. Suppose we can show not R implies C, where C is a contradiction. Do you remember what's a contradiction? What is a contradiction?
Always false.
Right, it's a statement that's always false in every instance.
It's like P and
Right? So if you can get to a statement something like P and not P, we know that that's always false. I use or here instead of the logical word. Right? That's a tautology, that's always true. If you turn this to an and though, that's actually always false. Right? So that's just some statement that, you know, it can never be true. It's false in every instance. There is no one, not even one example where this thing will be true, right? So here's a statement under consideration. If I can prove that the negation of that statement implies a contradiction. Here's a question. What does this say about R?
That it implies a totality, or
In terms of its truth value, can we know what it is?
well, we know that not R has to be false for that statement to be true.
R has to be.
Exactly. So what does R have to be?
True.
R must be true in this case. And so this is why. Why does it have to be true?
If it was false, then you would have true implies false, which is a false statement.
Right, because if R is false, then not R is true, then that means we would have true imply false as a proof. And we know it's not. Right? For the implication to work, we know there's literally one instance in which this doesn't work, and that's when true implies false. Right? Which means if I get something implying a false statement, that thing itself had to be false. But if not R is false, it must mean that R was true. And so I can prove the truth about a statement by looking at the negation of that statement. Let's pretend that it's false, right? So here's something I want to prove is true. Let me pretend it's false, and I'll show you that this leads to a contradiction, right? Now, if that leads to a contradiction, it means that the original statement was true, right? So as an idea, this can also make sense to people where it's like, this has to be true, because if it's not true, it means this, and you know that's total craziness. So you're forced to believe the other alternative, right? Sure, that makes sense intuitively, but we need to make sure it makes sense logically, and it does make sense logically. Based on the truth table, if you prove this is true, that has to be false, which means that has to be true. So it is a logical thing to prove something in this way. And so what this leads us to is a proof by contradiction. Basically assume what you want to show is true, assume it's not true, show that that causes craziness to happen, and then that will actually prove that the original statement is true. Not gonna do this. The idea to prove something is true, assume it's not true. Right? Very anti-establishment, very confrontational, very young and rebellious. That's why the kids love it. Assume it's not true and show this leads to a contradiction. Of course, you have to logically show this leads to a contradiction. It doesn't always lead to that. That's why, which, and again, you'll see people make arguments like this in everyday life, but they make it probably the wrong way. I was going to give an example, but in this climate, man, everyone's going to be offended. Some of you probably know what example I would use. But you'll see people like that. We can't do that because if that happens, then this is going to happen. And that's madness. Therefore, we have to do it this way. Right? We've heard this. If we allow them to do this, then this is going to result. And that's craziness. Therefore, we have to. Anyway, let's move on. It turns out, though, if you can logically Here's how to apply it to our important statement. Remember, P implies Q is a very important statement. It's often the kind of statement that we want to prove. You always have to assume something to prove something. Here's how to show P implies Q by contradiction. Right, so this is the proof technique now. To prove P implies Q by contradiction. I'm going to give you the steps. Is step 1, assume we are going to need to assume that this is false. Right? Now what does it mean for the implication to be false? When is the implication false? When P is true and Q is false is the only situation. So you're going to assume that P and not Q is true. Right? Or assume P and not Q. Right? Now you making that assumption is you assuming that this is not true. Right? To assume that an implication is not true means you're assuming the antecedent is true, but the consequent is false. Right? So that's the assumption. So that's how I'll know if you're doing a proof by contradiction. You're going to make this kind of assumption. You're going to assume the first part is correct, but the second part is not. Right? Now once that's your first statement, I know, okay, this person is setting up a proof by contradiction. 2, show that this leads to a contradiction. I.e., you want to show that P and not Q implies some contradiction, and when that happens, lightning strikes and it's impossible, so it must mean that this was true in the first place. So this technique is called proof by contradiction. Like all our proof techniques, has 2 steps, and the kicker is in the second step, right? The assumption part is the easy part. It's just a sentence, you just say this, right? Assume that this is true, show it leads to a contradiction. If that's the case, this must be false, but if that's false, this must be true, right? That falls from the truth. This is a proof by contradiction. Starts out with this kind of assumption, ends with that kind of assumption. Ends with that such a statement. So let's segue into this idea using one of our familiar proofs. So let n be in Z. And we know how to prove this by other means, but I wanted to do it by proof by contradiction. If 5n plus 2 is even, then n is even. Now to be clear, we know how to do this by other ways, right? Normally we would do this as a proof by contrapositive. But we're going to use proof by contradiction. Just for you to see how its structure can vary. We use proof by contradiction instead of the contrapositive. Right, which would probably be your knee-jerk reaction. Now on a test, I would assume most people go by contrapositive here. But let's actually do this proof. Proof. Assume 5n plus 2 is even, but n is odd. Right? Now in a proof by contrapositive, right, the one we've done before, what would the assumption be?
Assume n is odd.
Assume n is odd. This part wouldn't be in it. Right? But once you put that part in there, I now know you're doing a proof by contradiction. We're doing this. Right? So I'm going to assume the first part is true, but the second part is false. And I'm taking both of these claims to be truth at the same time. Right? So I'm claiming n is odd is true, and I'm claiming this is true, and I'm saying they're both true at the same time, but I want to show that it's not. Right? And so this is assumed true. This is assumed true. They're both assumed true at the same time. Okay. Now you want to find a contradiction. Since n is odd, n equals 2k plus 1 for some integer k, but then 5n plus 2 would be equal to 5 times 2k plus 1 plus 2, which is going to be 10k plus 5 plus 2, which is going to be 2 times 5k plus 3 plus 1, which is odd. And why is that a problem? Our assumption was it's even. I made the claim that it was even here. We assumed 5n plus 2 was even. In other words, we now end up with a claim where there's something that is both odd and even at the same time. That is a contradiction. Lightning strikes, everything breaks down. Yeah.
On the first step, why is it not right to say like 5n plus 2 is odd? And then,
Because this is what we assume. We assume P is true and Q is false. You have to do that, right? This statement here is the P. This statement here is the Q. We're saying if P, then Q, or P implies Q. If you're doing an assumption that you want to prove by contradiction, you assume this is true and assume that is false. So I made this assumption, and then pretending my assumption was correct, I concluded something that cannot possibly hold at the same time, right? I assumed something was even, turns out that it's also odd by this assumption. That's a contradiction. You can't be both even and odd. This is a proof by contradiction, right? Now, a proof by contrapositive, what that does is assume this is not true and shows that that is not true. Right? So in some ways you can think of it as a very limited version of a contradiction proof, where the thing that you're particularly trying to break is the P. A proof by contradiction, though, is very general. This contradiction can literally be anywhere in all of math. Right? You don't have to, it doesn't even have to be specifically about what you're looking at. It can be as broad as you want, and it gives you a lot of leeway, therefore. So a lot of people like that. Let's do another example. Prove there is no smallest positive real number. So this is like the guy that said, there's no such thing as leprechauns, right? There's no such thing as a smallest positive real number. Turns out you can prove that. Okay? You can't prove it with an example, right? Because it's a universal claim, but it can be proved that there does not exist such an example. So here's how such a proof would work. Proof. Assume to the contrary that there is a smallest positive real number. Call it X. Now here comes the crazy word. Consider. In this case, it's not going to be so bad. Can anyone tell me what to consider? Give me an example of something to consider.
X over 2.
X over 2. Let's look at half that number. Consider x over 2. I just took that real number and divided by 2. Since I divided by a positive real number, it would stay positive. Then, x over 2 is positive and in R, but x over 2 is less than x, which should be the smallest positive real number. Right? So I said, this is the smallest guy, but I found someone smaller. So I found something smaller than the smallest. That's a contradiction. There's a proof that there's no smallest positive real number. Give me any real number that's positive and tell me, this is the smallest one, I can find one that's smaller. Okay, that's the smallest one, I can find one that's smaller. Okay, that's the smallest one, I can find one that's smaller. Whatever number you tell me, I'll divide it by 2, and it still be positive, and it's still a real number, and it's still smaller than the example you gave me. Right? Meaning, if we assume such an example exists, it leads to a contradiction. Right? Another one. I was going to prove that one, but I think it's in your homework.
That's okay. I'll skip to a historical proof. So it's kind of a proof that someone has to tell you if you're doing a class like this. Maybe I'll go back to some more trivial proofs later. The square root of 2 is irrational.
That was a big one.
Now, this is kind of one of those proofs some of you probably know it already because it's a very famous proof. But the contradiction comes out of an unexpected place, and that's why a lot of people just like that. So it's important actually for historical reasons. It's kind of like when someone talks about teaching you differentiation, x squared is always one of the first examples they do. Oh, the derivative of x squared is 2x. That's like the first example everyone does. So this is one of the examples that everyone does when they're talking about proof by contradiction. Because it's people consider it elegant. It sort of comes out of nowhere. Okay, so here's how it goes. Proof. Assume square root of 2 is rational. Right? So this will bolster the example we gave before about the radical 2 to the radical 2. Radical 2 is actually irrational, and this is going to be a proof. Then, what does it mean to be irrational? It's a fraction, so that means I can write this guy as a over b, where a and b are integers, and b is a non-zero integer. Right? So making the assumption that this is false means it's rational, means I can write it in this form. Then, what that means is that I can square both sides. So this means that a squared is equal to 2b squared. You're like, okay, where are you going with this? We're going to see. Oh, I forgot the one little thing that's going to make the contradiction. Right? See, it comes out of nowhere that even when you know the proof, you can miss it. Right? we'll assume this is in lowest terms, right? So it turns out that every fraction we can reduce the fraction, right? We can divide out the common terms and cancel them. That's a thing we can do with good numbers. Okay. So I assume it's written as a fraction, and we might assume we reduce this fraction. So we canceled all the common terms. There's no common term. You see that, like, okay, and then they show you this and like, okay, where are we going with this? Here's the thing. This means a squared is even. And that is true by definition. It's 2 times an integer. Okay, but what does a squared is even mean?
It means that you didn't reduce A as much as you could.
Yeah, but what does it say about a? To get to that point, we're going to make that a statement about a.
Something we proved before.
Yeah, we proved it before.
Yeah,
If a squared is even, then
Force is even.
a is even, right? This is something we proved before. X squared is even if and only if x is even. But then, what that means is that a can be written as 2k for some k. Then, we're going back to this equation. We have that 2k squared is equal to 2b squared, which means that b squared is equal to 2k squared, right? Which means that b is even. B squared is even, which means that b is even. So, b is equal to 2l for some integer l. But, and here comes the kicker. This is where they wrap it up and bring it back to you, and you're like, whoa, I didn't see that. Okay. Right, because they get into all these calculations, they're like, okay, okay, and every step of the way you're like, okay, okay, that's true, that's true, that's true. And then they sort of end it with, that means that a over b, right, and this is radical 2, is equal to 2k over L. 2k over 2L, because my b is 2L, my a is 2k, which is k over L, which is in lower terms. That's where the contradiction shows up. The fact that we made this assumption that we can reduce this fraction, it turns out that that's not true. So if I assume radical 2 is a fraction, it turns out that that fraction will be irreducible, which means I can never get it into lowest terms, right? Which is sort of a weird place for the contradiction to come out of, right? So historically, it's a very nice proof. Your book probably does this proof. I'm pretty sure it does. But it's something that I want to show you guys. For historical reasons. Here's another historical proof, which hopefully I remember it now. I just thought of doing it today, and I don't remember if I remember it. But it's attributed to Euclid, so if I might botch exactly how he did it, but this was the main idea. Euclid's proof of the infinitude of primes. Infinitude of primes. That is the idea that there's an infinite number of prime numbers. You'll never run out of prime numbers. There's an infinite number of them. So primes have always, we know that a lot of people geek out about primes. Turns out that they can geek out forever. Right? You will never be done discovering primes. Okay? Right? So there are an infinite number of primes. And how he did this was a proof by contradiction. Reductio ad absurdum, I think is the Latin phrase for it. Right? It reduces to an absurd claim. Right? Here's the proof. Assume for the sake of contradiction that there are only finitely many primes. Let's label them. Call them P1, P2, Pn. There are n of them, right? So there's only a finite number of primes. Does anyone actually know this proof? What's the next step?
Consider another number.
Just consider, right? That word again, and you're like, oh my God. You know when you read that, something's going to come out of nowhere. Does anyone know what number he considered?
So one extra thing, one more.
One more than the product of all
Yeah,
of those. Consider this number. It's the multiplication of P1, P2, P3, Pn plus 1. So it's like, assume there are a finite number of them. These are all of them, right? There are n of them. Boom. Consider this number. Right? This is not prime. By assumption, right? You assume there are only finitely many of them. By assumption, since it is not in the list. Right? No, that P1 is not equal to that, right? P2 is not equal to that, P3 is not equal to that. None of the prime numbers are equal to that. So that number is not in this list. Which means, since we assume that these are all of the entire list, it means that that number is not prime. But Pi does not divide P for any I. So it's not a prime number in that list, but it's also not divisible by any prime number in that list, right? Right, because if I took P divided by P1, that wouldn't give me P1, P2, all the way to Pn plus 1 over P1. This would give me this integer plus 1 over P. That's not an integer, right? So it does not divide it, right? You'll always have a remainder of 1 when you divide by these primes. But that's actually the contradiction. That means P is prime. Since any composite number. Composite is just the number we call it that's not prime. Any composite number is the product of numbers. Right? You can reduce any number. If you want to factor a number, you can always find what's called a prime factorization. Right? Meaning any number is either a prime number or can be factored into a bunch of primes. You can always reduce a number to a product of primes. That's a contradiction. So if you assume there is a finite number of prime, you can always find another number that's not divisible by any of those guys, which means he has to be prime. Because no prime in all of existence can factor that. So that's a very important proof. Again, very historical. It's thousands of years old.
What?
Huh?
Thousands?
Yeah, Euclid. When did Euclid? Hundreds? It's thousands, right?
Well, we haven't done anything useful in years.
Oh. No, we have done useful things in years. It's just that no one knows about it. There's a difference. Yeah, it turns out what most people think of as math is really hundreds of years old. Like the math that we're doing today, no one really knows about. They'll probably learn about that in 2,000 years. People will learn about the math that's being done today, and they're like, oh, that's interesting. it's funny. People who aren't math majors go around saying, "Oh, I don't like math." They don't know what math is, really. You know, we've done more math in the last 200 years than in the previous all of civilization. You know, so it's kind of like to say you don't like math is not really an informed statement.
Professor Smith,
Yeah.
can you explain the idea after we create P? I don't really understand the idea of that proof it.
The idea is any number that is not prime can be factored into primes. There's something called a prime factorization. So, for example, take a number that you know is not prime, like 15. What is that?
3 times 5?
That's 3 times 5. Those are prime numbers, right? Or you can pick 20. You know, that's 2 times 10, which you know is 2 times 2 times 5. Right? Any number can be factored into primes. Right? So that's a theory. That's something we know. Right? We didn't prove that in this class, but that's something you can prove. Right? So anyone talking about primes would know how to characterize something that's not prime. Right? So there's a theorem that says, this is, in fact, it's a very important theorem. It's the fundamental theorem of arithmetic. That's what it's called. Right? So it's like someone who studies arithmetic gets to this theorem eventually at the end of the day, the fundamental theorem of arithmetic, kind of like the fundamental theorem of calculus. So arithmetic leads to this overarching theorem that all integers can be characterized into 2 groups, prime and not prime. Turns out that the not prime guys can all be factored into the prime guys. Right? And that's always true. So this is called the fundamental theorem of arithmetic. Every number can be factored into primes. It's either a prime itself or it can be factored into primes. Right? Which means this number, if I assume it's not prime, I know by fundamental theorem of arithmetic, I can factor it into primes. But the thing is, it's not divisible by any of the primes that I thought existed, which means it can't be factored into primes. I can't write it as a multiplication of primes, because that would mean I'd be able to divide by one of them. Right? So the fact that I can factor this into 3 times 5 means it's divisible by the 3. It's divisible by the 5. Right? So any composite number will be divisible by some prime number. Right? So assuming that this is composite means that one of the primes have to divide it, but none of them divide it, because you'll always end up in this situation. Which means it has to itself be a prime number. Which means here's a prime number that's not in the list of all prime numbers that you told me existed.
So the proof that
So the proof is any finite list of primes you make, turns out it's not big enough. So you'll always be able to get bigger, add one more, add one more, add one more, forever. Yeah.
So if all these logical techniques, like proved by contradiction, have they also just all existed for casually for like thousands of years, and
Oh yeah,
we just
yeah.
never use them until, or we as students in here,
What do you mean?
like, no. Or
You
just,
said proof by contradiction.
yeah, just all these proof techniques, they've just existed and never really been used.
Oh yeah, like what? Yeah, this is thousands of years old.
I think some of these
This
things
is
happen in real life.
Older than Jesus.
Yeah.
Huh? What do you mean happened in real life?
Like some of these like proof constructs, they like come up in real life.
Yeah, just like in conversation.
Yeah, like you know
Without
the
noticing.
rational thing. So it's like you have a friend and then he's trying to like say get advice from this other friend, but the friend's like, I don't think it's a good idea. Why? Because there's 2 possible cases, and then in this case you screw up, and then in this case you screw up.
But yeah.
It's something
Yeah, the thing is, in everyday conversation, arguments cannot make sense. Right? So in math, you really want to get to the idea that there's a logical basis for all our arguments that we can know is objective. It's not going to depend on what mood you're in, or if you just got dumped by your girlfriend, or you know the economy's collapsing, or he's not my president, or whatever. It's not going to matter. You make the argument, you know it's true based on an objective set of steps. And yeah, this was around for thousands of years. It's just that not everyone has known about it. And pretty much anything you do in school at this point has been known for at least hundreds of years. Right? Calculus you're studying in calculus class now, it's been established for 300 years. No change is made at all. It's never been appended to. But that's what we're learning now. Anyway, we're out of time. We'll stop there. I'll see you guys tomorrow. Of course, homework for chapter 4 is due tomorrow. Would it be too much to ask for chapter 5 homework as well?
Yes.
What? Tomorrow? Yeah. Do tomorrow?
I did everything I wanted to do in chapter 5. I mean, there's a few more examples here and there, but they're kind of silly. Okay, chapter 4 due tomorrow. We'll make chapter 5 due on Tuesday.